Yeah, hello.
Hello.
There is a Ratnakar who has registered for the course as well. So I'm waiting for him to join. Maybe he's having some bandwidth issues. Let's see. Let me message him.
I think it has already joined.
Yeah, he has joined. I can see his name.
No. Oh, can you? No, I don't see his name.
Okay, we can see. Yeah, he just.
And now he left. Yeah.
Yeah, I think he momentarily joined. Yes. Uh, Now he's trying to do it. Okay, he's here. Yeah, hello, Ratnakar. Can you hear me?
Hello, sir.
Yeah, okay, so you're on. So I have started recording. So let me share my screen. Get rid of all unwanted screens. And, okay, since Ratnakar was not here, so let me last time. So let me just kind of do a quick recap of last class's lecture. Okay, I don't know if you, I haven't uploaded the last class. Ratnakar, you did tell me that you listened, you only listened to the introductory thing. So far,
Yeah, proceed as if please proceed as you would proceed normally. I'll catch.
So okay. No, that is fine. But since it's a small class, I mean, I could do some adjustments though, so that should not be a problem. I'm not going to go through all the lectures. I'll let you. So I'm just going to tell you what we have covered so far. Okay. What we have covered is I went through a quick recap of propositional logic. I did, and its use for modeling real life artifacts. Specifically, we discussed, illustrated several examples of board game modeling. Modeling solutions to board games as using propositional logic. Okay. And I did an introduction to Z3, the SAT solver SAT solver, that is for propositional logic, for deciding propositional logic from Microsoft. Okay, and assign some problems for you to do, for the class to do using Z3. Okay. After that, we started, discuss. I introduced what model checking problem was, and the fact that model checking itself required three things, or in general, formal verification. In particular, model checking requires three things to for the process as input to the process. One is a model of the computation system that you're trying to analyze. Number two, a specification of the expected behavior of the system. Here, when I say a system, it could be either a hardware system, software system, or a combination of the two. And number three, of course, the third component is, which is the goal of model checking, which is to show that the model satisfies, does not violate any properties that you have specified as constraints on the expected behavior. The third, so this is the three components that will be the subject matter that we will be studying in this course. So in the last class, what I did was I introduced a model, the modeling formalism that we'll be using for modeling our systems, and that formalism is called a transition system. Okay. Yeah. So so this is what I already said. So these three things, and as in logic, the satisfaction, a model satisfying a property is denoted with this double turnstile symbol. And what model checking does is exactly check this given a model and a property that it satisfies. The model satisfies the property in an automatic fashion. And a model checking is the subject of devising efficient algorithms to automatically check these properties. Okay, so what kind of system properties, and what kind of systems and what kind of properties, so these are the kinds that we're talking about. It could be a controller that controls a traffic in a control system. It could be traffic lights should never be green at the same time, or it could be a network of gates and flip-flops implementing some hardware circuit, and you could, which is being controlled by clock, and then you can have those properties like these things stated, and or a traditional software code where you want to prove you assert certain things to hold good every time the control reaches a particular point in the location, and you want to prove that. Or it could be some concurrent program and properties that are relevant for multi-threaded programs and so on. Okay, so let me skip. So this is the formal definition of what a transition system is. Okay, and it's a three-tuple. First component is the set of states that your system could potentially be in, and the second component is something that characterizes the set of initial states from which the system can start its performance execution. And then a transition relation that relates to arbitrary states in this universe of states, which describes how the system evolves over time. So the transition relation abstracts the unit of time. So so what we're interested is in not only the static behavior, more specifically, we're interested in verifying properties or analyzing these systems by making properties that we'll verify that characterizes its behavior as the system evolves over time. Okay. And then we had some examples that we saw. So let me skip these things. Maybe I will show you this. Yeah, so for example, one way of capturing this system, this piece of code, is through a transition system whose graphical depiction I've shown here. Here, the states of the system are the different possible values that the variables in the program can take. We have made them range over natural numbers. So any pairs, tuples, pairs of values from nat cross nat will be represent the state. And the transition relation is, okay, the initial state is, in this case, is something where both x and y are 0. And the transition relation is, okay, we are modeling each transition here corresponds to the execution of the body once in the iteration of the loop. So that is the granularity that I've chosen to model this at, which is something that that is your choice. That is one's the modeler's choice. You can use this formalism to model things at different levels of abstraction, and that is your choice, to make. And here, each transition corresponds to one iteration of this loop, and that is what is characterized here in this thing that I've highlighted here. So, given a state, a current state S, this precisely specifies what the next state can be as prime. So in this case, as it says, it must be something that where the x component of the successor state S prime has to be x plus 1 mod 3, and the value of y in the post state has to be x plus whatever x is in the post state, that plus 1. Okay, so this way of specifying a transition system, the initial state, as well as the transition relation, as by using formulas, in this case from first order predicate calculus, is what we refer to as a symbolic representation of the transition system. Okay, is that clear? Okay, so any questions so far? Okay, so I take that as a no. Okay, someone said something.
Yeah, can you?
Yeah, we are okay.
Yeah, we are okay with it.
Okay, fine. Yeah, so then I started talking about some concept called non-determinism. Non-determinism, you've already taken theory of computation, etc. There's non-deterministic automata. Okay, so whenever there is multiple possibilities, usually it's called non-deterministic, correct? So when you can have multiple successive states, but the reason I want to draw special attention to this thing is in the manner in which we use non-determinism, in the process of modeling. Okay, non-determinism is used to abstract, to throw away certain details. Okay, and that is there are two kinds of non-determinism that we use. To initial non-determinism to allow for the system to start with potentially multiple initial states. Okay, so the initial state does not have to be unique. And we also use it to model the environment. Okay, For example, the environment, if we don't want to specify how it has to change, since the environment can change arbitrarily, so we can make it non-deterministic. So those inputs which we will include as part of the state, the environment modeling in this formalism is also done by including whatever inputs that we get from the environment as part of extra components, as part of the state, as extra components, and we'll define the transition relation in such a way that it doesn't constrain the inputs from the environment at all, or you can constrain it as much as you want, and that is another way that we use non-determinism. And sometimes we use non-determinism to throw away some details about the certain aspects of the system itself. So by, for example, in concurrent, when you model multi-threaded or concurrent programs, so the process that is chosen to execute the next time is determined by the scheduler. And say you only care about analyzing this concurrent programming system, irrespective, you're verifying those properties that you expect to be true, regardless of the schedule for scheduling these processes that an operating system uses. Then you could do that by modeling the concurrent system by completely hiding the scheduler. And that you can do it by making the transition relation itself non-deterministic, so that you can there can be multiple next states possible from current state. Okay, so that's what I was illustrating here. So in this case, we are saying that okay, we want to say analyze the behavior of this piece of software for starting from arbitrary initial states. Then you could make the initial state to be true. Okay, so here, although I've shown this to be arrow, this is a mistake. So when you make the predicate characterizing the set of initial states to be true, that is what it exactly means is that any state can be an initial state in S. Can be an initial state, so which means there should be an arrow to all the states, and the relation remains the same. So you could start from any state, and then so that's what this thing means. And the yellow portion here gives you the state that you will end up with. Okay, of course, here even every white colored one has to be yellow, because that is included in the initial state. Okay. And then we were talking about modeling this clocked hardware. So here the state variables are the state holding devices, the 2 bits of this register or flip-flop, and A and B. And reset here is an input. We are throwing away the clock by making each transition correspond to the state changes corresponding to a tick, 1 tick of the clock. Okay, so the next state is for this system is a function of the current state as well as the input, and that's what is given here by the delta function. Okay, so I've exactly described what the next state ought to be, with the next state as far as the A and B component of the next state are. So as a function of these 3 bits A and B, which are the current state of the register, and the input. Now the question is, how do you model the input, which is part of the environment? Okay. Now, you could have an extension of the transition system formalism where inputs are treated in a special way, which is like, for example, here, sometimes they use these what are called Mealy machines, okay, to do it. But in our formalism, what I'm trying to illustrate is that the whatever the environment which the inputs to the component inputs that is to the system can also be included as part of the state. As you see here, the state now has an extra bit to denote reset. Okay, and what I'm doing is, and obviously there will be more states here since a reset is also included. So there will be twice as many states as if you, as it's shown in this model here. So, but the thing where non-determinism is being used is, as you can see, the A and B component are getting changed as per the delta defined here. Okay, so this one counts. This is a counter. It counts starting from the initial state, which is 0, 0, and it is a mod counter. So it is mod 3 counter. So the A and B component, the first two bits here, change to 0, 1, and I have used non-determinism to allow for reset to be either 0 or 1 in the next state. Okay, so when this is a synchronous system. So when I say clock is thrown away, it's thrown away, it's abstracted away. So in a synchronous system, everything there is supposed to be a global time. Okay, and that is supposed to keep ticking at a certain rate, and everything, the state as well as the input, which is part of the environment, is supposed to change at that as per the global clock. So a transition here in that sense models a single tick of the clock. And as you can notice, I've allowed for, since reset, the system is not constraining in any way how reset can change. So reset can be asserted to at any point in time. So that's why in the next state I've allowed for the possibility that reset can be either 0, 0, 1. And as this, whenever reset is asserted, it is supposed to reset the state back to 0. That's why there is a transition from each of these states back, where reset is 1 back to 0, 0. Okay, so that is the point that I was making, that you could use non-determinism. But you can model environment by including whatever all the components in the environment, the inputs, as part of the state itself, and use non-determinism to and define the transitions to the environment as part of the transition relation itself. Okay, this way of modeling is where I call this system has now been, which is an open system, has been combined with the environment to produce a transition system and models it as a closed system. We will see later on that one can model the environment separately and the system separately, and then kind of use composition of rules of composing transition systems to get the combined transition system. Okay, so yeah. So any doubts here? Any questions here?
I just wanted to ask, by closed system, did you mean that it has no inputs?
Correct. Yes.
Oh.
So if I left this system with reset as okay. So for example, I could have here, what is the environment here? By the way, if you were to model the environment as per this what I've shown here, how would you model the environment as a transition system. So the environment has one reset. Okay, so you will have. I cannot draw the thing. So maybe I will. Yeah. So it will have what the value of reset is what the state of the environment is, and in the next state it can so there's a 0 and there is a 1, and there is it would be something like this. So if you were, so you could have a 0, and there will be an arrow going to 1, okay, and there will be a back arrow here. Correct? Okay, there'll be 2 states in which there's a transition from 0 to 1, or 1 to 0. Okay, so that would be the oh, I'm sorry. This is not correct. Okay, so there'll be a transition from 0 to 1 and 1 to 0, as well as self transitions from 0 to 0. There will be a self loop from 0 to 0 as well as 1 to 1. Correct? Okay, because the next state, the next value of reset could be either 1, or you can go from 1 to 0, or it can stay in 0, and it can also stay in 1. So that would be what I call as a separate modeling of environment. Okay, and then you will you could still model this thing as so a reset here. So there is a way you could model the reset. You could include it as an input. Okay, and then you can have a separate system for the environment, and you can have a certain way of composing these systems. Okay, so, and we will get to that. So the answer to your question is yes, a closed system is where I have the entire thing in a monolithic way of modeling it as a single transition system. Okay, both the environment as well as the thing. So that is sometimes is what is referred to as a closed system. Yeah, or you can model different components of a system by itself as a transition system, and then you can have some ways of rules for composing the individual transition system to come up with a thing, and that's how one has to do in practice for this transition system formalism, modeling formalism, to scale in practice. And we will see how that can be done. And when you get to that composition, there may be different ways that you can compose depending upon certain aspects of the system, and that especially relates to synchronous, asynchronous, and different kinds of composing rules. But when I say it is a closed system, what I mean is that all the components of the system are merged into a single merged into the states of the intertransition system, one single transition system modeling the whole thing. That's what I mean by a closed system. Does that answer your question?
Yeah.
Okay. Yeah. Yeah, so the reason I showed this picture is because this is a kind of a modeling of an open system. Here, as components of the state, I'm only including the state holding devices of the system. And reset is, I've explicitly indicated as something coming from another system, which has its own transition system, okay? And there could be two modules that are sending outputs to each other, okay? So, and then, I mean, that way, I mean, the system is dependent on an external input, okay? But here, we don't exactly say how reset itself can change, okay? So that can be specified by a different system. So now, in that case, this kind of modeling is where what I call is an open system modeling. So where I allow for certain inputs to be free, okay, in this case, okay, and that there can be another transition system that governs those things, and then we need to have to specify ways of composing those two things, which we will do later. Okay, so assumptions, some critical assumptions that you should be aware of in our formalism. So, like I said, the transition system is a three-tuple, okay, which has the one components giving the units of all the states, the set of initial states, and the transition relations. Domains must be large enough to include all possible values that the state variable can potentially range over. And transition relation has to be defined as a total relation, okay, on its domain, okay, on S, which means that it has to be defined for all things. Now, is this restriction? Actually, no, okay. So the reason is, why would you want to have a transition relation, the non-total? Okay, one reason that you might want to have is maybe there are systems, because a transition relation is, as I told you, is indicating how the system evolves over time. Okay, so for example, but you could envision systems which terminates. Okay, there are terminating programs. So there could be certain states, specifically the terminating states of a terminating program for which there is no successor state. So by making transition relation total, are you restricting the ability to model certain behaviors, say certain kind of systems, say terminating systems? Actually, no. Okay, because you could, if indeed there is no successor state, as in the case of terminating state, you could pick a special state. Okay, either you could say, oh, I'll continue to be in the same state, or you could pick some special state in which you go and then you continue to be there. Okay, so you could encode that behavior, using a total transition relation. So for the development of the theory of analysis, model checking, it makes our life easier to make the transition relation total. Okay, and that's what we'll use. And where it comes in the way, like in modulating terminating systems, we will use some special way to encode the fact that it is terminating, as I have shown here. The other thing that we'll assume, as I've already indicated, is that the set of states is discrete. And I say finite here, although the model checking as a concept and even as a thing doesn't necessarily require that your system be finite. But most of the algorithms the techniques that we will study in this course, they're applicable for finite state systems, where the transition systems are finite in the sense their state is finite, but it can be arbitrarily large. Okay, so that is one thing. Okay, as I said, model checking framework and methods are still applicable for infinite state systems. But for infinite state systems, unless you make certain assumptions, decidability is not guaranteed. So but the techniques, can still be applicable, but in the sense that it may not, those algorithms may not terminate. Okay. Um, um, so for convenience, we will say that we will look at, we'll restrict ourselves to finite state systems, and we assume either they are presented as a finite state system or they're abstractable to a finite model. And I'll tell you I'll illustrate what exactly I mean by this thing, abstractable to a finite model. Okay. Let's take this. This just illustrates how we model terminating transition relations. So the original system the code that I had while true. So therefore that was a truly non-terminating program, correct? Okay, that's why it had a loop in the thing, between these two yellow states, okay? And it was non-terminating. But this program is a terminating program, so in which case you can extend the state to some special states, and then you could use that, from where you will that you end up with. This is I could call as a terminating state, which corresponds to the state that you get after exiting the loop, and you can still use a formalism to make the transition relation total by just using the convention that I will continue to stay in the same state. Okay, so that is the convention that we will be using. So any confusion or doubt there? Yeah.
In the example you showed here in the diagram below, here also the transition relation is not total, right? Because the first state and the third state, those two yellow circles are not related, right?
Of course, I have not shown all the other states, okay, which need to be included. Otherwise, your comment refers to which one of the yellow states?
Yeah, first one and the third one. X is equal to 0, y is equal to 0, and x is equal to 2, y is equal to 3. Those both the states are not related, right?
Oh, no, that's not what I mean by total. Total means it has to be total, like a total function. It has to be defined for every possible combinations of values for x and y. Because of course it is defined for 0, 0, because there is the transition relation there is an outgoing transition. Okay, it's only when there is no outgoing arrow from a state that I call it as not total. If it is not defined, if the transition relation ignores to define a successor state for any particular state, any state, that's when it is not total. Okay. Why do you say this is not total? Yeah, a total function means it has to be defined for every possible value in its domain. So here, what is the domain of the transition relation? It is the cross product of x and y, correct?
Yes, sir. Yes.
So the pairs of x and y.
Yeah.
Okay. Yeah.
And the first one, the last one doesn't have
correct. The last one, for example, here does not have an outgoing edge, and I'm just showing a convention that we will use to make it total. And so you can either say I will take all terminating states into one, and then I'll merge them and I'll have a transition from there. That is one way to do. Okay, so whatever it is, that will be part of your modeling convention. Yeah, so that we will keep the transition relation total. What I have not shown here is all the white states. Okay, for this. So obviously the transition relation will be defined for all the unreachable part of the states as well. Okay, in this case, all of them will be divided into certain. So there will be arrows from those. Those
I have a follow-up question here. In the previous slide, you said that the number of states will be finite, like that. But here, adding those white color states it's a cross product of a natural number, so it will be infinite.
Correct. Yeah. So that's, yeah, you're right. How, what does it mean to make a conversion? To how do you, so your question is, how do you abstract that into a finite model? Okay. What does it mean to even abstract that into a finite model? And that is the question that I will be getting to in the next few slides. Yeah. How do you do that? Okay. And what does it mean to do it? Okay, of course we can always make it into a finite system, but you will have to do it in a way that it is something that your analysis or your prediction via your analysis method should still be applicable to the infinite states. Okay, and that is what I'll explain what I mean by that. Yeah.
But here, like x and y have int values, right? So like that would be finite, right? For int.
No, why? Why will it be finite? If I assume that if I make x and y range over NAT, there's potentially infinite number of positive.
Yes. If
states. Yeah.
If you do it for NAT, it will be there, but usually int will have like a domain, right? A finite range.
Why?
Right?
Oh, no. Why?
Why
do you say that?
For each language, it will be there, right? Like a finite range.
No. You're right. The code itself. If what you mean by is you're modeling C code, then it will be finite. Okay. Then your domain is not exactly NAT, but it will be bit vectors or something like that, or a finite subset of NAT. I mean, what if in the ideal case, okay, suppose I want to model infinite precision. Okay, in reality, that may not be there. Okay, but you can imagine I don't want to constrain myself to finite states. Okay, or for that matter, if I want to do real numbers, I mean, you're right in that in practice, if your intent is to only model C code or any particular code in a particular language, then what you say is correct. But I can argue that I want to model infinite states systems for its own sake. Okay. I mean, there are systems where you want to not restrict you want to predict behaviors as though if they were real numbers or integers and so on. Okay. So you can imagine such wanting to do that and analyze such systems and prove certain properties. See, in a way that I'm already, you can see I'm giving out the punchline kind of a thing. So anyway, that's how I answer your question. Okay. I mean, but you still, that doesn't mean that that doesn't negate the fact that you want to model infinite state systems and then have, properties checked for that. So how do you do that? And the other question that I'm raising is, for example, in this case, I mean, I'll tell you, I mean, that leads to the Kripke structure definition that I have right now. So, see, in this case, it really doesn't matter. Because I start with 0, 0, as a matter of fact, it doesn't even matter. So I could, for example, I mean, suppose this is NAT, I still use NAT, okay? Now, I can partition my state space into those in which x and y are less than or equal to x is less than 3 and y is both, I mean, they are less than or equal to 3, for example, and all the other states in which their x is greater than or equal to 3 and y is greater than 3. Okay, I could kind of have only 4 partitions. Okay, so and then then I can kind of collapse that infinite state system into just these these finite partitions, okay? Those partition in which, I'll have explicitly for those parts in which x is less than or equal to 3 and y is less than 4. There, I will keep each these tuples separately, and I will merge all those other states, which in this case are not reachable, okay, into one symbolic state, okay? Since I'm representing these things as symbolically. So that is the idea. Now, that abstraction, that collapsing, just here I'll keep all the yellow states and I'll merge all the white states into one symbolic state, which can be represented by the formula x is greater than or equal to 3 and y is greater than 3. Correct? All those are the ones that are not, reachable, okay, or potentially not reachable, okay. And I can do that. I can then draw a transition system. Now that kind of an abstracted system is good enough for me to verify a certain property. Suppose what I want to verify is check is that x and y will always be less than or equal to 4 or something like that. Okay, that is preserved by this state. So that, collapsing all those states into one is good enough for me to verify if my limited aim is only to verify certain properties like x is less than or equal to 3. Okay, so then it doesn't matter, what the other thing is, and I think this requires some thought. A little bit of thinking. So if your properties are sometimes restricted, then it is possible to only focus, kind of get a finite representation. Those things that don't distinguish that properties, those states that don't distinguish those properties can all be collapsed into one. So based on your property, you can actually collapse an infinite number of states into a single symbolic state and still analyze that infinite state. Okay, so that is the key idea that that we will be using, so that this finiteness restriction is not going to in practice disallow you to analyze infinite state systems. Now you can analyze infinite state systems without doing that abstraction, but at least what I'm saying is that is one way to deal with infinite state systems, using if the properties that you care to verify allow you to do that abstraction, collapsing of the thing in terms of, then you can use it. If that is not the case, then you will have to have different set of techniques. And what I'm focusing on is those to analyze those systems which are inherently finite, or which can be or infinite state systems which can be abstracted into finite state systems. Okay, so yeah, so let me, yes.
Can every segment of code be, does every segment of code have a finite state abstraction? For example, if I change the last line to x minus 1, won't it be infinite state? No?
Yeah, so no. I think it's not a function of the property, of the operations that we use in the code. Okay, it's actually what you want to verify. Okay, so hold on to your question there. So let me introduce what is called a Kripke structure next time, and then we will get back to this question, and I think you will understand why. So answer to your question is, you'll not be completely convinced, but no, even if you do x minus 1, first of all, okay, now, well, if you're doing x minus 1, you have to define it. I said we are using the NAND domain, okay? X minus 1 will, what is x minus 1 on that?
No, I meant if we change it to x minus 1, we get infinite set of values, right? Won't we? Because y less
No,
than
no, no.
2.
Even with zero, you're getting. Yeah, I mean, yes, yes. No, no, no. The point I'm making is, even if I had, okay, yes, if you did x minus, if you did x minus 1, you will be getting infinite set of values. Yeah, and then okay, let's suppose I did x minus 1 here. So then y's value will be infinite, correct? Okay. And you know, once you extend this to integers, say, okay, then, okay, first, yeah. So, wait a minute. Yeah, no. So even here, okay, so let's see. Let's get to your question. Suppose y is equal to x minus 1. X's value will only be between 0 and 2, correct?
Yeah.
So what will be y's value? It will be between minus 1 and 1. So in this case also it will be finite, okay? In this particular case, because at most what it can be, I mean, it can be minus 1 to 2, correct? Yeah,
right,
but
right.
that is not the point in this case. But that is not the point that you were trying to say. Okay, I understand. I can easily make this. You know, in this case, because I made y to be dependent on x, I could, you know, it will remain finite. Okay, but that is beside the point. Let's suppose I change this to y is equal to y plus 1. Okay. Now, in this case, also it will be finite because I'm restricting myself to y less than equal to. Let's suppose that I go to, since we are, discussing this particular example. So let's suppose that I change this to my original program, while 1, okay? And then I make this, the second statement is y is equal to y plus 1, yeah? Then it will be truly infinite. X's value will still be finite. Y will be infinite, correct?
Right.
Yes.
Now that is a truly infinite state system, yeah. You know, and in yeah, so even here it is infinite, but the infinite parts is not reachable. Okay, but that is a simple case. So there, at least the infinite, it is truly infinite. Okay, because every component of the infinite states, since y's value is infinite, it is indeed reachable. Yeah, even from 0, 0. Okay, an infinite number of states is reachable. But suppose that I really don't care. I mean, the one that I want to verify, the property that I want to verify is if x is less than or equal to 3. I mean, less than 3, less than or equal to 2. Then I can truly, if that is all the property that I want to check, is it even relevant to keep y? I'm using the case where while 1, okay, not while I'm using the original program. While 1, I do this, and y is equal to I'll have y is equal to y plus 1. Okay, and if the property that I want to verify is that x is less than or equal to 2, then it really doesn't matter. If you think about it, I can throw away y completely. Okay. And only keep track of x, and then it'll be a finite system. So the point that I'm making is you should focus on the property. Relative to the property, it doesn't matter. The y's value is irrelevant, and therefore you can throw away certain components. And in some cases, you can even reduce it to finite systems. So that is if the if certain things, if in this case they are certain predicates, they are make certain states indistinguishable, then you can actually, I mean, you cannot do it in all cases, but I'm saying depending upon the property, and that is the one that we will capture. See, it is easy for me to say, oh, we will restrict ourselves only to finite state systems. So, and the method is there. But there is since we're discussing modeling, that's why I'm bringing this issue, okay? That there are ways to make, depending upon the kind of property that you want to verify, there are ways to throw away information from the system, and you can still prove those aspects of the system. By aspects, I mean the properties, by only abstracting those systems into a finite system. And that is the point that I want you to appreciate. And we will see the means for you to do it explicitly here. Okay. So let me get to the thing. Hold on to any further questions. Yeah. So what are crypt key structures? So this is a logical concept. Okay. So it's kind of an extension of what we have defined as a transition system. So sometimes a crypt key structure is also called a labeled transition system. So in addition to the three components that you already see as being part of the definition of a transition system, we have a label for each of the state. This label assigns a finite set of atomic propositions to the state, for each of the state. Okay. Another way to look at it is a predicate. And the important thing to recognize is that AP is a finite set of atomic propositions. Okay. So that is a finite set. Okay, and therefore you can view it as a predicate that is either true of S or not. So why label these states? They denote certain basic facts that we care about, that we care to track in the states and their truth value evolution over time. And remember that even if there are infinite number of states, these atomic propositions are only finite. Okay, so when you make the atomic propositions finite, it actually kind of induces a partition, a finite number of partition for on S. Okay, and then we study the temporal properties over how these truth evaluations for these predicates change over time. Okay, and by making these things as finite, that is what gives you the ability to kind of abstract away things for those particular properties. Okay, and as we will see, it will also provide a link between the actual behaviors and specification. Okay, let's see some examples. Okay, so in your modeling, when you model certain systems, of course, you have to think about the state variables as the important variables that you want to that form the component of states. What is what each of those variables, the values, the set of values that the variables range over, and that you will have to pick large enough to accommodate all the states. And picking these labels as propositions will give you, it is not the modeling aspect, it is the modeling, the property. Okay, what is the property that you focus on? Okay, and that is kind of, in a way, makes this formalism, even when you apply to infinite states, makes it, it provides a way to abstract it to a finite system. So and this label, choice of the label is also left to the individual task at hand, and that is, via these labels, you choose the set of properties that you care to represent and analyze. Okay, so let me take these the original set of examples that I had. Just hang on one minute. I want to keep track of the time as well. Sorry. Yeah, so I still have 10 or 15 more minutes, so this should be okay. So we have these systems. So traffic lights should never be green at the same time. So what I mean by labels here is, so in this case, of course, the state. Oh, what is this? No. Oh, no, I will get to that. This one does not have. Oh, maybe. Yeah, for example, the labels here can be, these atomic propositions could be that if in a state it is, okay, see, in actuality, in your system, you might have lots of different states, but as far as the property that you care about is whether the state is in green, is a green state, or a yellow state, or a red state. Okay, that is good enough. So labels in this case are those predicates that tells given any state. So in reality, the model can have lots of other things for you to control here, but your labels might that you want to express the property relative to may have only 3 things that you care about the state at the propositional level. Similarly, here you only need to care whether it is your predicate, your label should be can be just if it is less than or equal to 3, and so on. Okay, so yeah. Let me now introduce a few more concepts here. Given a Kripke structure, a label transition system, there are 3. There are things. So there are something called, we talk about something called executions, traces, and behaviors of a transition system. So a linear execution of a transition system is an infinite path through the transition system, starting from an initial state. Okay, so that is it's a linear execution starting from an initial state. How you execute. It's a infinite sequence of states. Notice that you can have infinite sequences even on a finite state system. Correct? Because they can be loops. Yeah, they can be loops in the system. So it is any sequence of states, any infinite sequence of states, such that the first state satisfies I, and each successor state is related by your transition duration. So that's what's called a linear execution. And a branching execution is an infinite tree of states, such that the root satisfies S0, and every SI. So there are 2 ways of viewing evolution, is what I'm introducing. I'm defining. Okay. So as an example, so now a trace. This is what is called execution. So when we talk about systems, we refer to linear executions or branching execution. Okay, so so whereas a trace of a transition system is a labeled execution, TS induced by the labeling function. So for every execution here, if I just apply the labeling function on each of those states, what I get is what I call as a trace. Okay, so here it will be a linear trace, or it's a branching trace. Okay, so and a behavior of a transition system is the set of all traces originating from all initial states of TS. Okay, so that is a set. So this is from individual execution. Individual trace is something starting from a particular state, and the behavior is the set of all traces that originate from any possible initial states. Okay, so for example, suppose I, the linear behavior of a transition system example here. So I'm using this transition system, which is the same as what I introduced earlier, this infinite loop thing, but starting from an initial state in which y is 0, but x can be less than or equal to 1. Okay. So this is the transition system. So because I'm allowing two initial states here, 0, 0 and 0, 1, I'm assuming that x and y range over that. So what you get is, this is the reachable component of the system. Okay, so remember that. So these are defined, the behavior, execution, and whether it is linear branching are defined only for the initial states. Okay, therefore, what are the linear executions of this system? So some linear executions. So here is I'm giving the linear. Okay, and suppose my labeling functions, they are x less than 3 and y is equal to 1. Okay, I mean, when I choose a particular labeling function, at the basic level, it makes a choice for me as to what is it that I'm tracking. Okay, so in each state. So here, say I'm only interested in tracking if x is less than 3 or y is equal to 1. So this is what I call as the linear behavior is the set of traces, correct? That's what I've defined. The behavior of a transition is a set of all traces originating from all initial states. So from here, I only keep track of this. So there only these two are the only way. So if I start with x less than 3, then it will be I can only reach a state which is x less than 3, x less than 3, and so on. So the execution. So this is keeping track of how my predicates, the truth value. So traces are keeping track of how my truth value of the predicates are evolving as the system executes. So as you can see, these are the only two possible traces that can be there in the in the behavior. Okay. In either you start from a state from x is less than 3 and y can be this is it can be anything, but then you can think or so here I should say y is equal to 0. No, but I'm not even keeping track of y is equal. So x is less than 3, and then so this is 1, and once I reach x less than 3, y 1, then the same thing continues. Okay, so and now I can what my specification can be will be expressed in terms of these will be some constraints on this traces. Okay, that's how I will express. Okay, so then branching behavior will include it's a tree. So from each state, I'll keep track of both specific concurrent successor states. Okay. So and here so if I care to keep track of only whether AB is less than or equal to 3, then my traces will be just the labeling of those things, and then my specification, what I call a specification, will be expressing only certain behaviors are allowed or not. So they are defined as properties. What I keep calling as properties are defined as constraints over these acceptable behavior. Okay, so behavior is a set of traces, and executions are real executions. They are just set of states, sequence of states or trees of states, or traces are keeping track of the labels of the states, and we will define formalized properties as constraints over these behaviors, and the logic that we'll be defining for specifying these properties will be some temporal, will be a certain special kind of temporal logics. Or later in the course, we'll also look at ways of constraining the behavior by using a special kind of automata. Okay. So I will stop here, and I will take any quick questions. Okay. So I will I know that I rushed through this last part of the thing, but I will do a recap next time. So any questions here?
Sir, in the previous slide, can you just repeat what assume meant? Like what was assume of? Yeah, at the top of the slide, you had assume y equal to 0 and x less than equal to 1.
Yeah, that's another way of just saying my initial state is that. That's all. Okay. Sometimes, okay. So in an actual programming language, if you want to start from a state in which, I guess you could say, I mean, you could either not have not initialize variables. I mean, you can start from an uninitialized state, which is usually you won't do it. Okay, usually you end up in a program. Okay, this okay. I just wanted to capture the fact that I'm allowing the program to start in an arbitrary state, not in an arbitrary state, but in any one of the states that satisfied this condition. Okay. And since there is no way in a real programming language, usually real programming languages don't allow you to do this. There are some programming languages that allow you to have assert and assumes. Okay, so assume just means, oh, let's assume that I'm constraining myself for y to be 0 and x is less than or equal at this point. That's what it means. Yeah.
Okay.
That was a convenient way for me to translate that into my initial state. Okay, that's all. Any other questions?
Could you go to the specification slide? The specification part. No, slide before this. The specification. Yeah.
Correct. Yeah.
The GE of x less than 3. I'm not sure I follow.
Yeah. I think there's a lot of notation here that I skipped. Okay, one way, I mean, I didn't get to the fact that I mentioned about temporal logic. Okay, so you kind of got the idea of what traces are, right?
Yes.
So executions, they are actually a real sequence of states, whereas here, for the linear behavior I'm talking about. So let's restrict our linear behavior. Yeah, trace just keeps track of the truth value for those predicates. Okay, so in this case, it's the linear behavior. Now, let's suppose, if you can notice, okay, what the specification, what we really define as specification is specifying constraints on these behaviors. Okay, so for example, here I might want to say that every possible trace in every possible trace, legal trace should be such that x is less than 3 in every. My behavior, the system behavior should be such that in every trace, in every execution, every state that you get should be such that x is less than 3. Okay, that's how you do the specification. That is, it can include only those traces in which every state has to satisfy x less than 3. Okay, that is what this thing specifies. Okay, now that is the kind of ability that we want to be able to specify and then verify. Okay, this one is saying what is called forever property. Okay, in every tray, in every possible trace that is generated by the program should be such that x must be less than 3. X must be less than 3. It is sometimes called forever. Okay, x must be less than 3 forever. Okay, in all the executions. So, for example, here I'm saying, oh, eventually every possible trace that is in every possible expected trace, y should eventually become 1. Okay, is what this thing is stating, which happens to be the case here. Okay, because these are the only two possible. Every execution can be mapped to one of these two traces. Okay, so here y itself is 1. Oh, there's something wrong.
Yeah, in the initial state, y will be 1, right?
No, actually that's wrong.
Oh, y equal to 0.
Yeah, y should be 0. No, this is wrong. Okay, there's a mistake here. Yeah, there's a mistake
The
here.
second one is
it should be the other one.
X.
It should be 1. It should be 1
Yeah.
0. Okay, it should be 1 0. Okay, and 0 0. So this should be flipped, 1 and 0. And here it should be y cannot be 1. Okay, so it should be x less than 0. Y is not 1. Sorry. So, but eventually, so in this case, y will eventually become 1. It may not stay 1, okay, all the time. X will certainly stay less than 3 all the time. Okay. Y will, the thing that I can say about y is y will eventually become 1. Okay. As a matter of fact, I could say even more than that. Okay. So from every y will become 1 infinitely many times, kind of thing. So y will eventually become 1. Once it becomes once it is not true, y is not 1, it will once again become 1. Okay, that is also another thing that is true of all the traces that belong to this. Okay, yeah. So that's how we state. So what exactly is the property or a specification is these are formulas. Expected behavior of what traces can be included, is allowed, is permitted in the behavior, and what traces are not. Okay, that is what the specification does. Yeah.
So will we have the specification beforehand?
Correct. That's right. Like I said in that slide, in model checking slide, there are 3 components that you need to have before you can actually do the process of model checking. One is the model.
Yes, the property.
Yeah, the initial state and the property. Okay, so I have actually introduced the formalism for specifying the model. I'm now initiating you towards what it means to specify properties. Okay, towards that end, I first introduce you to what are the kind of behaviors that we care for. Okay, so linear behavior is one thing, and then I introduce you the thing. What we care for is how these predicates, the basic atomic predicates, which say certain facts about certain things that are true in a state, how they evolve over time. That is what I'm tracking. Yeah, and a specification you'll see will be defined as a constraint on the kind of behavior that are permitted for the system and that are not permitted. Okay, that's how it will be defined, as a constraint on a linear. And given that should be given a priori. Given that, then the task of model checking is to show that every possible behavior from any initial state, every possible traces that is included in the actual behavior indeed satisfies the constraint that is defined by the property that forms the specification. Okay. Yeah. So the property, the specification will specify constraints over these acceptable traces. Yeah.
Yes.
And yeah, so that's what we will define the property. Now, specification can be, as you can see, because these are, I mean, my behavior are traces, in this case, linear traces. So you could as well formalize the specification as the acceptable language of an automata. Okay. Or you could devise special purpose logic, okay, to say whether and the satisfying instances are these traces. And so that's why there are two ways of doing it. You can either use an automata as the tool to make the specification. That will give rise to automata-based model checking. But if you use a specialized logic to express your specification, then you will use logical methods, okay, to do this. We have already seen how logic can be used to capture the different components of a transition system. We will also see how behaviors can be modeled, and then how we'll introduce. Next thing is, I will introduce temporal logic, two kinds of temporal logic, to specify these constraints on these traces, okay, or sets of traces, as a matter of fact. Yep. So any questions, further questions? Yeah. Yeah, I want you to, I haven't given a date, okay? So, if you do those examples on SAT, okay? I have uploaded, by the way, the Python interface, a document that gives the Python interface a guide, a tutorial to how to use the Python interface on Moodle, okay? And I want you to review that, and then you will be required to use that for your first assignment, okay? And I will formally upload the assignment, but I want you to get started. And the first assignment will be doing those exercises on SAT Solver. Yeah.
Yes.
Yeah, okay, sir.
Yeah, please get started on that. And once we upload, I will discuss the assignment as well. Yeah.
Could you also upload the lecture video of Wednesday?
I will do that. Yeah, I will do that. Yes, that. I think I will do it promptly. Yeah.